In this first module of Chapter 10 involving applied demography, I show 8 different ways to compare the life table properties of 3 different fruit fly species, including the Mediterranean and Mexican fruit flies and the vinegar fly Drosophila. Comparison number 1, survival graph. Here's a graphic of survivorship of the 3 species of fruit flies. We have age on the x-axis and survival LX on the y-axis. The sketches of the 3 species reveal the major differences in size. From the largest to the smallest, left to right, we have Mexican fruit fly, the Mediterranean fruit fly, and Drosophila. The Mexican fruit fly is the longest lived, with a median survival age of nearly 2 months. The Mediterranean fruit fly and Drosophila survival probabilities are virtually identical until about 1 month of age, at which time survival in Drosophila exceeds that for the medfly. Comparison number 2, survival metrics. This graphic sets the visual stage for the next comparison where we have specific life table metrics. That's comparative number to involve the survival metrics where we have fruit fly species in this top panel and the metric labels in the leftmost column. We start with the metrics of central tendencies, including the mean, which is the expectation of life at adult emergence, the median, which is the age at which 1/2 of the original cohort are dead, and the mode, which is the age at which most deaths occur. The results show that the Mexican fruit fly is the longest lived with respect to all 3 of the central tendency metrics. The expectation of life for the Mediterranean fruit fly and Drosophila are roughly similar, averaging around 2 weeks. The next group of metrics in this table on cohort survival are the ages at which the cohort survival in these 3 species is 0.75, 0.25, 0.10, and 0.01. As expected with the earlier comparisons, the ages at which all of these survival thresholds occur are substantially later in the Mexican fruit fly than either the Mediterranean fruit fly or the Drosophila. These metrics are similar for these latter 2 species. The last set of comparisons for the second group of metrics involves the duration between the ages when 75% of the cohorts are dead to the age at which 25% are dead, and then again from 10% to 1% deaths. In all species, these durations are roughly similar, ranging from 2 to 3 weeks. Comparison number 3, mortality graph. So underlying survivorship schedules are, of course, mortality schedules for each of the 3 species. You see at the bottom again we have age on the x-axis and age-specific mortality QX on the y-axis. The highest mortality occurs in the Mediterranean fruit fly, the lowest in the Mexican fruit fly, and an intermediate mortality for Drosophila. Mortality in all 3 species is low and roughly comparable at the youngest ages. Their schedules then diverge at intermediate ages but reconverge at around 60 days when approximately 10% daily mortality is occurring. Note here in the upper left survival graph that despite the convergence of the mortality schedules, earlier differences in mortality resulted in major differences in survival to these older ages. Mortality schedule differences between the Mediterranean fruit fly and Drosophila are shown here, where they are essentially superimposed as they increase at the same rate for the first 3 weeks. However, the rate of change with age and mortality for Drosophila then decreases and thus departs from the mortality schedule for the Mediterranean fruit fly that continues to increase at a relatively high rate with age. Comparisons of mortality in Drosophila and the Mexican fruit fly reveals that their schedules diverge substantially at the very early ages, with Drosophila being substantially higher rate than the Mexican fruit fly for nearly 2 months. And finally, the large difference between the Mediterranean fruit fly and the Mexican fruit fly are shown here, with, for example, mortality at 40 days for the Mexican fruit fly at roughly 2% daily, but over 7% daily for the Mediterranean fruit fly. Comparison number 4, the Gompertz mortality model. As you can recall, the Gompertz mortality model is given as mortality at age x, mu x, equal a e to the bx, where a equals the initial mortality and b equals the exponential rate of change with age. And doubling time of mortality equals the natural log of 2 divided by the exponential rate b. Here's a table containing the best fit Gompertz parameters for the 3 species, and for perspective the graph of the age-specific mortality for each. Note that we have across the top fruit fly species, including the mexfly, the medfly, and Drosophila. Then in the first column, the Gompertz parameter or metric, including the initial mortality rate A, the slope B, and mortality doubling time dt. Note that the initial mortality rates A for the mexfly and the medfly are virtually identical, whereas initial mortality rate in Drosophila is much lower. The slope parameter B for the mexfly is only about 0.03, whereas the values of this Gompertz parameter for the medfly and Drosophila are 3 to 4 times greater, which is to say mortality is increasing for these species at substantially greater rates with age. The same relative differences apply to doubling time comparisons since this time depends on the value of B. Thus, doubling time for the mexfly is over 3 weeks, whereas for the other 2 species is only around 1 week. Comparison number 5, life table aging rate denoted Kx. Life table aging rate Kx is the rate of change with age in the central death rate Mx, where Kx equals the log of Mx plus 1 minus the log of Mx. This gives a graphical comparison of the life table aging rate for the 3 species, in which age is on the x-axis and life table aging rate Kx on the y-axis. These red lines are at a value of 0 as a baseline for indicating no change in the rate of mortality increase with age. Because of the hugely variable pattern in the middle graph for the life table aging rate for the Mexican fruit fly, I will set that aside and just use the top and bottom graphs showing Drosophila and the medfly fruit fly Kx values. Changes in mortality in the early ages from adult emergence to about 30 to 40 days for both species was positive, but decreasing. After around 40 days in both of these species, the change was substantially reduced, showing a pattern of mortality leveling off, especially for the Mediterranean fruit fly. Comparison number 6, mortality ratio. In this comparison, I examine the ratio of the Drosophila age-specific mortality, Qx, on this same schedule in the medfly. Again, we have age on the x-axis, and we have mortality ratio on the y-axis. A ratio of 1.0 indicates identical age-specific probabilities between the species. Note that the green shaded regions correspond to the ages at which mortality in the medfly is higher than that in Drosophila. This ratio also shows, first, the magnitude of between species mortality differences, and second, the crossover age of mortality at around 60 days, after which age Drosophila mortality exceeds the medfly mortality. Note the small graph to the right that shows the absolute differences in mortality rather than the relative differences as shown in this main graph. Comparison number 7, mortality contributions to differences in expectations of life. Let delta x denote the change in expectation of life between 2 cohorts from age x to x plus 1. LAX, LBX, EAX, and EBX denote the survival to age x for cohorts A and B, and expectations of life for cohorts A and B, respectively. Then delta x equal A minus B, where A and B are given by these respective equations. This graphic depicts the mortality contributions to the differences in expectation of life between the Mexican fruit fly and Drosophila as an example comparison. We have age on the x-axis and fraction of life days contributed on the y-axis for the 10.7 day difference in expectation of lives of these 2 species. This rightmost graphic again shows the mortality schedules for these species as a reference. The differences in mortality in the early ages favors Drosophila for a small proportion of the overall difference in life expectancy. However, the vast majority of mortality differences contributing to the life expectancy differences occurs between around 10 days and 40 days of age for these 2 species, as shown in the blue shaded areas of both graphics. You see here that a substantial but yet smaller proportion of these differences in life expectancy occur due to still very large differences in mortality from ages 40 to 60 days, as seen in the rightmost graphic of mortality. Very small contributions in favor of the Mexican fruit fly life expectancy occur at 60 days and beyond. So the carry-away message here is that mortality that occurs in the 1 month period between 10 and 40 days of ages in both of these species accounts for the vast majority of the between species life expectancy differences. Comparison number 8, mortality equivalencies. The last comparison between species is what I refer to as mortality equivalencies. The question is this: what are the between species differences in the scales of mortality for equivalent life expectancies? Formally, this can be shown with these equivalencies. That is, a modified QX for species A equals the product of 1 plus the scalar that I denote as delta in the original age-specific schedule for species A. The value of delta is adjusted so that the modified expectation of life for species A equals the expectation of life of species B. And we do the same with the value of the scalar delta to adjust mortality for the species such that modified expectation of life of species B equals the expectation of life of species A. Here are the results for this comparison of all 3 fruit fly species. We have the value of delta scalar on the x-axis ranging from minus 0.5 to 1.0. which when inserted in the equation will reduce the mortality by 1/2 with the former and double it with the latter. And then we have expectation of life on the y-axis ranging from 0 to 60 days. The top, middle, and bottom lines are the outcome of adjusting delta through the full range from minus 0.5 to 1.0 for the mortality schedule of each of the species to compute the adjusted expectation of life at emergence as an adult at each intermediate value as well. Comparison number 1 shows that Drosophila mortality must be reduced by 1/2 for expectation of life in this species to equal the expectation of life in the Mexican fruit fly. This scale can be contrasted with the 0.8 reduction in Drosophila mortality for this species' expectation of life to equal that of the Mediterranean fruit fly. Mortality in the Mexican fruit fly would need to be doubled for its expectation of life to equal that of the Mediterranean fruit fly. And mortality in the Mediterranean fruit fly would have to be increased by 1.4-fold in order for its expectation of life to equal that of Drosophila. This ends this first module of Chapter 10, in which I provided an overview of 8 different approaches for comparing the life table properties of different cohorts.